Okay, I think we can start. Gives me pleasure to introduce this week's DTM seminar speaker, Dr. Maximilien Verdier-Paoletti. Max. Maximilien came here. Sorry, because it's webcast or something. Anyway, Maximilien got his bachelor's degree and a master's degree at the University of Paris, and followed by another master's degree at the University of Versailles something, after which he got his PhD in cosmochemistry at the Museum of Natural History in Paris, working with Mathieu Gounel, and working on interesting projects with carbonaceous chondrites that he's going to talk to us about. In January, he joined us here as a postdoc working with me on various projects regarding pre-solar grains, which hopefully they'll have a chance to talk to you about. Are you talking about that at all today? Okay, well, hopefully he'll give us another seminar in a year or two on the interesting research he's doing here, but for today we get to hear about what he's done before. So, Maximilien.
Can you hear me? Yeah. So thank you, Larry, and thanks to all of you for coming today to see this seminar. So as Larry said, I'm going to talk a little bit about what I did during my PhD in Paris, and I will try to present to you two studies that we did during those 3 years. And I know that many of you don't work on meteorites, and maybe even few of you work on aqueous alteration inside meteorites. So I decided to do quite a large introduction to try to get everyone into the scientific context and to try to expose the tools that we used, because the two studies that I will show today rely mostly on oxygen isotopes, and I don't know if everyone has already worked with oxygen isotopes. So just to start with my introduction, I will go on from a very broad perspective to a smaller perspective. So starting with what you may already be familiar with, that is the solar system. And as you know, we have the inner planets and the outer planets in the solar system that are separated by a large belt of asteroids. And asteroids are rocky bodies going from meter to kilometer scales and coming in very different shapes, attesting for their collisional and dynamical history, such as the cosmic diamond, Ryugu, on which the two landers of the Hayabusa mission landed successfully last week, I think. I think Larry is more aware of this than me. And those two asteroids are considered to be the remnants of the planet formation in our solar system, and therefore they are also considered to be the witnesses of the birth of the solar system. And when you study those bodies, you can see that they come in two different kinds. The differentiated bodies that formed early in the solar system and gathered a lot of radioactive material that led to an intense heat event that led to their melting and to a differentiation event that gave them this very specific constitution, similar to the one of the inner planets. So they've got an inner iron core and a rocky mantle and a rocky crust. And of those three constituents, we've got fragments that reach the Earth that are differentiated meteorites. And on the other hand, we have the undifferentiated bodies that are called the primitive asteroids because they preserve the primordial constituents within them, such as the chondrules and the refractory inclusion, on which I will come back later. And inside the asteroid belt, it can occur that the asteroid meets in a relatively high velocity event that leads to the disruption. And some fragment might get on Earth-crossing orbits and reach the surface of the Earth. And one classification for those fragments follows the same one as for the asteroid. So we've got the undifferentiated meteorites and the differentiated meteorites, and the indifferentiated meteorites right here that are called the chondrites. And all those meteorites forms families in which you can have different subgroups that are defined based on the chemistry, the texture, and the mineralogy of those different meteorites. And if you have never seen one of those samples, when you're looking for them in the desert, it might look like this. So it's kind of darkish, brownish rock that is quite heavy, that it's more dense than what you expected. When you pick one up, you feel that it's more heavy than what you would have expected. And if it has been around for a long period of time on Earth, it might get a little bit reddish like this because of the iron getting oxidized due to the weathering on Earth. So it's not that easy to identify them because if they are quite fresh, they can be very dark and they can look like terrestrial rocks. So it's not that easy, and this is quite a big one. And this was an ordinary chondrite that we found in the Atacama Desert in 2015. So when we look at those chondrites, we can see that they form different families, and one of the most studied families is the Carbonaceous one. Why is that? It is because we think they are affiliated to carbonaceous asteroids that constitute a very large fraction of the material in the asteroid belt. It's one of the most common material, and we think that it might have been the most common bricks for the formation of planets. So studying those meteorites might give us a lot of information about the primordial components of planets. We think they are affiliated to these asteroids because of their spectral similarities with them in the visible and near-infrared wavelength. And with the two ongoing missions, sample-return missions that are Hayabusa 2 and OSIRIS-REx, that will try to sample those bodies, it will be very interesting to try to compare the fresh material coming back to us with the material that is in our collection. And another reason why we study those meteorites is because chondrites represent the largest fraction of samples in our collection today. And when we look in the different groups of carbonaceous chondrites, it exists one group that is called the CEM chondrites. And this is a group that I've been studying the most during my old PhD. And many people have done it before me, and for many different reasons. They represent a significant fraction of the falls of the meteorites. The falls is when you witness the fall of the meteorite, so it can be quite fresh. While on the contrary, you can have what we call founds that are meteorites that are found randomly when you're working in the desert or in Antarctica. Their composition, like most of the carbonaceous chondrites, is very close to the chemical composition of the solar photosphere, which attests for their pristine nature. And finally, they are quite rich in water and in amino acids. And this makes us think that they might have contributed to the incoming material that led to the emergence of life on Earth. But the main message here that I need you to remember for the rest of the talk is that they are still considered as relatively pristine material because of their link to primitive asteroids. They are constituted of four main constituents. That would be the chondrules, which are spherules of silicates, olivine, pyroxene, and a glassy mesostasis, iron-nickel alloys, and refractory inclusion very rich in calcium and aluminum that are considered to be the first condensed solids in the protoplanetary disk. And therefore, we were able to date the solar system thanks to those refractory inclusion. And those three components are cemented in a very fine grain matrix with grains of hundreds of nanometers that would be crystalline, olivine, and pyroxene, amorphous material with composition between olivine and pyroxene 2, and organic matter. But when we look more closely to the mineralogy of those bodies, we can see many different minerals attesting for secondary processes occurring in the parent body. And it can be thermal metamorphism or aqueous alteration when we see oxides, carbonates, phyllosilicates, or sulfides. So how does this process occur inside the parent body? Well, the big picture would be that during the accretion and after the accretion of the body, the short-lived radionuclide would generate a heat event that would melt the surrounding ice around the crystal, or the ice filling the porosities of the asteroid, because those bodies can be quite porous, between 30 to 50% porosity, and sometimes up to 80% too. And once the ice melted, the fluid will interact with the rocks inside of this, lead to dissolution of primary minerals, and finally to precipitation of secondary minerals. And therefore, the primordial information about the physical chemical condition of the protoplanetary disk that might have been retained inside those primordial constituents are lost. And it's therefore very important to try to understand how this process occurs inside the asteroids to try to better characterize the different reservoirs involved in this process. And this could lead us to also understand a little bit better the dynamical history of the protoplanetary disk. So to understand, to constrain how this process occurs, it is important to characterize the meteorites that we're working on, and specifically the intensity of the secondary process that they experience. So it exists many different scales to try to constrain this, but all fit one old scheme that is the one of von Schmussenwood in 1967 that states that a pristine meteorite would be of degree 3. And from degree 3 to degree 1, aqueous alteration would increase in intensity, while from degree 3 to degree 6, thermal metamorphism would increase. And when you look at the CM chondrites, you can see that they span the whole range of aqueous alteration intensity available today in our collection. And in 2007, Rubin and collaborators described another scale that can describe sub-degrees of intensity inside the main one. And this is based on the amount of anhydrous material remaining and iron-nickel alloys remaining, the chemical complexity of carbonates, and also the chemical constitutions of secondary phases that are tertullinite, cronstedtite intergrowth that are sulfide and ferrosilicate mixed together. So with all those tools, many different teams have tried to constrain how alteration occur inside the parent body. And it exists many different models, but no consensus today. And many models state that it existed fluid flow, either on the centimeter or micrometer scale or to the kilometer scale, such as water exhalation, convection, or more recently, the mud bowl model of Planck that states that once the ice from the porosity is melted, the asteroid turned into a big ball of mud in convection due to the heat gradient. But another kind of model states that water was static, probably not on very large scale, probably in microenvironments of hundreds of micrometers due to the very low permeability of those meteorites. And when you look also at the timescales for those processes, you can see that it seems to span between 2 million years up to 15 million years after the formation of the first solids. But when you look at most of those estimations, you can see that they relied on the carbonate datation using the manganese chromium radiochronometer. And the problem with those measurements are that they need a very, very specific standards that we don't have today. So the uncertainties on those timescales can't be quantified precisely at this time, and they have to be taken lightly when it comes to the datation of this process. So if I just want you, just before I go into the first study, to have a broad picture of what is the scientific context surrounding this study, it's that we still don't have any consensus about the fluid flows inside of the asteroids, and the condition in which it occurs are still poorly constrained. The range of temperature involved, the chemistry of the fluid, or even the ice contents that leads to the amount of water available for this are still unknown. And we don't know what is the main factor controlling the intensity that we can see in the different samples for this process, and we still don't know precisely over which time scale it occurred because of the lack of standard. So during my PhD, what we wanted to do is to approach the problem following 3 different ways. First, we wanted to develop a new tool to try to constrain the temperature range in which it occurs, and then we wanted to try to identify the main controlling parameter for this intensity, as well as to see if impacts would be the process that starts aqueous alteration inside the asteroids. And finally, we tried to develop a carbonate standard using high pressure, high temperature experiment. And this is still work in progress, so I won't talk about it. And if I have time, but I'll doubt it, I will try to talk a little bit about pre-solar grains. We'll see how it goes. So the first study about the temperatures of aqueous alteration, I'd like just to start with the scientific context on this one too. For many decades, it has been studied inside carbonaceous chondrites and specifically CM chondrites. And for a long time, aqueous alteration has been considered to be a very low temperature process, between 0 up to 25 Celsius degree, with some excursion around 70 and 80 degrees. And then in 2015, Connell worked on carbonates inside those meteorites by dissolving the carbonates using phosphoric acid and measuring their carbon isotopic composition and their oxygen isotopic composition. And he stated that aqueous alteration occurred between 0 up to 130 degrees Celsius. So it changed a little bit the paradigm over, of this temperature range for this process. All those studies, at the exception of the one of Baker, relied on carbonate oxygen isotopic composition, phyllosilicate oxygen isotopic composition, so secondary minerals and oxygen. Why do we look mostly at calcium carbonates? It's because they are considered to precipitate directly from the fluid and almost don't evolve afterwards when it comes to their oxygen isotopic composition. So they are considered to be a direct tracer of the chemical and isotopical composition of the fluid from which they precipitate. And unless you dissolve them to form later a second generation of them. And why do we look at oxygen isotopes inside of them? So we look at the three main oxygen isotopes that are 16, 17, and 18. And mostly because it seems to exist two main reservoirs of those in the solar system, and with the solids being very enriched in 16 oxygen, while the ices at the origin of the fluid would be heavily enriched in 17 and 18 oxygen. And we think that the composition of secondary minerals is a result of the interaction, the degree of interaction between those two reservoirs. And here I'm not considering organic matter too, which seems to have a very wide spread in oxygen isotopic composition. So for those of you that don't work with isotopes, I don't know if there's a lot of you around here, just a quick vocabulary of how we use those isotopes. So you'll see a lot of delta notation in my graphs. It's just to represent the excess or depletion of heavy isotopes in our sample relative to a standard here. And those variations can be very, very small, so it's in per mil. And I will also talk a lot about fractionation factor that just describe how the isotopes are distributed between two interacting phases. And usually we show this in a 3-oxygen isotope plot with, on the X scale, the excess or depletion in 18 oxygen relative to terrestrial standard, and in the Y scale, the same for the 17 oxygen. And if you look at papers, at cosmochemistry papers working with oxygen isotopes, you always see two main trends. The first one would be the terrestrial fractionation line that represents the line where all the oxygen reservoirs on Earth would fall along. And it also has a slope of 0.52, which is characteristic of a mass-dependent fractionation process, meaning that the repartition of the isotopes during the process relies only on the mass of the isotopes involved. And this is usually equilibrium effects or kinetics effects and a lot of geological processes such as condensation, evaporation, melting, or precipitation. And the second trend would be the Carbonaceous Chondrite anhydrous mineral mixing line. And this does follow a slope very close to 1, and it's characteristic for mass-independent process, such as radioactive decay, nucleosynthetic anomalies, irradiation effects, photochemistry, or mixing between two different reservoirs. So now that you've got the tools in mind, I'll go right into the study of how we tried to get the oxygen isotopic composition of carbonates. Because in the study of Connell, it just dissolved a whole bunch of rocks and dissolved different kind of carbonate and get the global oxygen isotopic composition for carbonate. And we wanted to do something similar, but at the mineral scale. So we took 9 different CM chondrites that sampled the whole range of aqueous alteration degree available in our collection today, going from the Paris meteorite, which is the least altered CM chondrite that we've got nowadays, to a CM1 chondrite that is completely altered with no anhydrous mineral remaining. And we acquired ADS maps of all those meteorites to look for carbonates inside of those. And then we determine their chemical composition using WDS, and we go on and we went to Nancy in France to use an ion microprobe, a synth 1280, that works exactly the same way as the nanosims here, almost exactly the same way as the nanosims here. It's a mass spectrometer that enables you to get the composition of a single mineral in a big sample. So how does this work? We usually focus an ion beam, an incident ion beam, which could be cesium or oxygen, that sputters the surface of the sample away. So there's a bunch of particles that are ejected from the sample. And using a set of magnetic lenses, we extract the ions that we want. And those ions are conveyed into an electrostatic sector that will filter them based on their energy. And then they will go into a magnet that will filter them based on the mass over charge ratios. So for a different mass over charge ratio, we've got different trajectories that lead the specific mass into a specific detector. And that's how we are able to get the counts for 16 oxygen, 17 oxygen, and 18 oxygen. But these instruments has to be calibrated the best way possible to get a mass resolving power that enable us to discriminate between interferences and the real signal. If you well resolve the two, for instance, for 17 oxygen, there is a contribution of 16 oxygen hydrides that we want to resolve. And if it's well resolved, the space between those two beams will be large enough for those two different beams to enter the detector at different time and give us two well-separated mass spectrum. That these two mass spectrum are easily identifiable. And if it's not well resolved, the two beam will get into the detector at the same time at one point and will get a weird-looking mass spectrum where deconvolving the signal would be very hard. So based on this, we determined the composition of approximately 90 carbonates in the 9 different CM chondrites, and these are our results. So you can see that our result fits very well the result from the literature here in dark gray, and they seem to not follow a 0.52 trend. So that means that the composition of carbonate might not be due to a mass-dependent process. And when you look at the bulk oxygen isotopic composition of the same chondrites, we can see that it seems to describe a trend that is exactly similar to the one of carbonates within those, a continuous trend. And when you look at the phyllosilicate composition in the matrix, well, it fits right here, following the exact same slope. So you've got the bulk, the matrix, and the carbonates that define a trend that we call the BMC for bulk matrix carbonates that seems to follow a trend of 0.66. And this means that we cannot assume that carbonate composition is due to mass-dependent process, but rather to a mass-independent process, meaning that carbonate's composition is a direct tracer of the degree of interaction between the very 16O-rich silicates and the very 16O-poor fluid that comes from the melting of ice. And what we saw also is when you look at the literature, it exists many different oxygen isotopic composition for water inside those CM chondrites, either determined based on the carbonate and phyllosilicate composition or from direct measurements by stepped pyrolysis on a very freshly fallen meteorite. And when you look at those data, they define a highly correlated trend that is almost exactly parallel to the BMC trend. And this gives us a lot of information. The first one would be that all the CM chondrites seems to have shared the same thermal history. If it wasn't the case, it would mean for all the different CM chondrites with different thermal history, you would have a couple water BMC trend that is different from the one in another CM chondrite. But it's not the case. All the chondrites define the same trends, either in water or for the minerals. And that means that they have the same thermal history, and this could suggest that they all come from a primordial single parent body and from the same initial material for ice and solids. And the other information it gives us is that we can retrieve the oxygen isotopic composition of the fluid from which secondary minerals such as calcium carbonate precipitated. And as it is precipitation, if we assume that it's done at equilibrium, we can assume that it follows a slope of 0.52. And if it is a mass-dependent process, it's function of the temperature. So this is what we did. We developed a new way to get the temperature of precipitation of every single carbonate inside our chondrite. So how does it work clearly? So you've got those two trends for the water and for the bulk matrix carbonates. And when you take one carbonate inside this strand, you can assume that it should be related to an oxygen isotopic composition of water here by a slope of 0.52, since precipitation is a mass-dependent process. So the intersection between a slope of 0.52 linking a carbonate of a very specific composition, this gives us the oxygen isotopic composition of the precipitating water. And since mass-dependent processes are a function of temperature, we can retrieve the temperature precipitation of the carbonate following those two different, following this law that we got using the fractionation coefficient between calcite, which is a calcium carbonate, and water. And this is what we did. We did this for all the carbonate that we measured. And then we did, and for the phyllosilicates in the matrix too, using the adequate law. And we did Monte Carlo simulation to get an average estimation of the temperature precipitation. And this is what we get. For carbonate, it seemed that the average precipitation temperature would be around 113 degrees Celsius plus or minus 54 degrees Celsius. While for the phyllosilicates, the serpentine, it would be around 74 degrees Celsius plus or minus 1 degree. The very small errors here are due to the fact that those measurements of phyllosilicates have been done by crushing meteorites, extracting the matrix, and then getting the oxygen isotopic composition of the matrix only. So it's bulk measurements, and the whole material is destroyed, and the error bars are way smaller than the one acquired using a SIMS on our carbonates. So this explains the larger errors for carbonates compared to phyllosilicates. But this is an average estimation, and we can get the temperature precipitation for all our carbonates. So, and sorry, one last thing is that the difference in temperature seems to suggest that most of the carbonates precipitates before phyllosilicates. And this is consistent with mineralogical observation where carbonates are slowly replaced by phyllosilicates in a lot of different CM chondrites. And when we look at the temperature, and the large variation is due to the fact that our carbonates do not follow a single line. It's scattered around this trend. So when we calculate their temperature of precipitation for each carbonate, we get this trend going on from minus 50 degrees Celsius to almost 275 Celsius degree. And 75% of the carbonates precipitate above 50 degrees Celsius. So it's hard to consider aqueous alteration and specifically very low temperature process in the asteroids, because also almost 50% of the carbonates precipitated above 100 degrees Celsius. And another thing, and the last thing that we can say about this study is that when you look at the capital delta 17O average composition for the carbonates inside all those different CM chondrites, so the capital delta 17O is just the difference between the composition of the carbonate relative to the TFL composition for the same delta 18 value. We see that this parameter seems to correlate with the intensity of alteration. That means that the less altered is a meteorite, the higher will be the oxygen isotopic composition for its carbonates. And when we look at this parameter versus the average temperature precipitation of carbonates inside those meteorites, we can see a correlation too. That means that carbonates inside the less altered meteorite have seen the highest temperature formation. And this means that all the CM chondrites seems to share the same peak temperatures, but that the more altered ones have seen the process of alteration maybe for a longer period, long enough for the precipitation of carbonates to record the dissipation of the heat inside the parent body. So if I had to conclude on this first study, that would be that it seemed that all the CM experience the same similar thermal history, and that they all experience the same peak temperatures too. And this could be explained with a single parent body, or at least with a single parent body with the same initial material. And most of the Ca carbonate seems to precipitate at higher temperature, at least at temperature way above the 25 degrees Celsius that were suggested for several decades. And it seemed that most of those carbonate formed before phyllosilicates too, and this is consistent with the observation of carbonates being replaced by those phyllosilicates inside meteorites. So it's possible that the range of temperature is way wider than what we were expecting first. And it would be interesting to try this on other kind of carbonaceous chondrite now to see if we see the same thing. So this was our first study. And then we wanted to try to constrain a little bit better this problem, the process of aqueous alteration in chondrite. And to do so, we looked at a very unusual meteorite that has been very poorly studied. It fell in 1930 in ex-USSR, close to the village of Boriskino, and is therefore called Boriskino. And it looks like this. So all the CM chondrites are what we call breccia, meaning that they can have different lithologies inside a single fragment. Lithologies, different material with the same composition, so that might come from the same parent body, but with different geological history. And usually when you look at a sample of a meteorite, you don't see that much clasts within it. You can see one or two or inside a very a thin section. But here you can see plenty of those with different colors, with different textures too, and different kind of mineral within them. And this is very unusual, and this might be one of the most heavily brecciated chondrites that we've got nowadays. And I think this is why many people didn't want to look at it, because it might be a little bit too complicated to study and to understand. So we look at different thin sections from these meteorites, and what we can see is that we can still see those different classes within it, and we identified 7 different lithologies that seems to be always in the same sequential distribution, with the B lithology in the middle, what we call the B lithology in the middle, with a little bit of it at the top right corner, and surrounded by the A and C lithology, and with the E and D lithologies at the same place. And how we approach this meteorite, well, first we wanted to determine specifically, accurately, the degrees of alteration inside each single class. And then we wanted to try to see if it was temperature or the abundance of water available that determined the degree of alteration inside those different lithologies. And finally, because of all those classes and this very, very unusual constitution for a meteorite, we wanted to see if hydrothermal alteration was linked in a way to impact process and so to brecciation. So first, what we did, we wanted to use the tools given by Rubin and collaborators in 2007 in each different lithology. So we look for anhydrous, the amount of anhydrous minerals, the amount of iron nickel, the carbonate complexity, and the chemistry of secondary phases that are TCI. And the problem is that it seems that those tools are not precise enough to accurately determine the degree that they described. And this is because mainly one of the main parameters is the chemistry of TCI, and TCI are really, really integrose, phyllosilicate, and sulfide, and there can be huge variation of the FeO over SeO2 ratio inside a single crystal. And this can't help us to determine the degree of alteration. And it seemed between 2 different sections and in the same lithology, the variation in iron nickel can fluctuate by a lot, like %. So it's not those different parameters cannot be used to precisely describe the degree of alteration. So what we did is we assumed that since it's classified as a CM2, well, all lithologies are CM2, at the exception of one, which is very, very different from the others, and this is the B lithology. Why is it so different? Well, because when you look inside of it, there is no anhydrous mineral remaining at all. Even the chondrules, which are constituted of mainly olivine that is pretty resilient to alteration, are completely pseudomorphized by phyllosilicates. And we did not see any iron nickel metal in all the B lithologies that we had. If you want to compare, this is what would look like a very lightly altered chondrule in a CM chondrite. You've got a lot of olivine in the middle, big crystals of olivine, a little bit of pyroxene at the edges, and a glassy mesostasis, and some spheral of iron and nickel metal remaining. But this is not what we see. The other thing is that when we look for carbonates inside this lithology, we only see dolomites. And dolomites is the carbonate that we only see in heavily altered CM chondrites, going from the degree 2.2 to the degree 1. So this also attests for higher intensity of aqueous alteration. And finally, the last thing is the morphology of all the sulfides inside this lithology. They all have an acicular morphology, which is quite unusual in chondrites and has only been seen in CM1 and CI1 classed in brachias. So those three components certify that the degree of alteration in the B lithology is degree 1, while the rest would be CM2. And so using those two information, we decided to try our new tool for temperature inside of this. So we look for carbonates in those different sections, and in the different lithologies. And this is what we get. The calcium carbonates here, described by circles, follow the exact same trend that we have seen in our previous study, with a slope of 0.63. So it means that we can retrieve the temperature of alteration following the same procedure. But what is interesting is when we look at the dolomites isotopic composition, because we can see that their oxygen isotopic composition is the lightest of all the carbonates that we have. That means that they precipitated from a fluid that has interacted more with the rock and got more enriched in 16 oxygen. So this is consistent with a higher degree of alteration too. But they also fall along this global trend. So using another fractionation factor, the one for water and dolomite, we can get their temperature of alteration. So these are the results. What we can see is that for the dolomites in the CM1 lithology and for the calcium carbonates inside the CM2 lithology, we can't see a clear distinction in temperature range between those different lithologies. So this would suggest that temperature is not the controlling parameter of the intensity of alteration. So we wanted to try to constrain the water to rock ratio, the initial water to rock ratio for each single methodology. And this is very hard to get. Many people try in different ways, and one of them is the one given by Clayton and Maeda in 1984 that relies on the oxygen isotopic composition of the initial fluid that they determined to be 30.3 per mil, and the initial composition, oxygen isotopic composition of the rock, the initial rock. And this is assumed to be the same as the one for anhydrous minerals, which is around minus 4.52 per mil. And then you need to have the fractionation factor between water and serpentine, so phyllosilicates, at their temperature of formation. And their temperature of formation is assumed to be 70 degrees by Clayton and Maeda, and this is consistent with our measurement that states that it should be around 74 degrees Celsius. So at this temperature, the fractionation factor would be 8 per mil. And we need also their oxygen isotopic composition. And this, we can't get it for each single different lithologies because we would have to extract a very specific lithology from the whole sample, crush it, get the matrix, and measure the matrix independently. It's a tremendous work, and that is sensitive to a lot of uncertainties too. So what we did is that in each lithology, we looked for a carbonate that precipitated at approximately the same temperature as phyllosilicates. And therefore, we were able to retrieve the precipitating water oxygen isotopic composition. And we assumed that this water also formed the phyllosilicates. So using the coefficient factor, we were able to get the oxygen isotopic composition of phyllosilicate in each different lithologies. And it seems to be always around 12.5, 12.7 per mil. And this is exactly almost the same value as the one measured directly by Clayton and Maeda that was 12.4. So we have all this, and then the last thing we need is the fraction of altered work inside the lithology. So for the CM1 lithology, everything is altered. There's no anhydrous minerals remaining. So it's a fraction of altered work of 1. While in the CM2 lithology, what we did is we did point counting inside of them, and every time we fell on the secondary phases, we counted it as altered, and every time we fell on an anhydrous mineral, we counted it as unaltered. And this gave us an average value of 0.61. So it's a work with a lot of assumptions, but it's also the only way that we got now to estimate approximately the water-to-work ratio. And this gives us a water-to-work ratio of 0.45 for the CM2 lithologies and 0.75 for the CM1 lithologies. So this would mean that the degree of alteration is not dependent on the temperature, and the chemistry of the fluid might be a minor parameter to this extent. The main parameter would be the amount of water available, and this would mean that water is the limiting factor here in alteration, which is what we would have expected. And finally, the last thing that we wanted to see is that does it exist a link between impacts and alteration, meaning does impact start alteration in the parent body? So Boriskino is a perfect sample to study this because of all the different classes within it. And when you look at the boundary of class, like here or here, you can see a lot of foliation features, such as this one. You can see that anhydrous minerals have cracks that seems to be perpendicular to the foliation plane. Chondrites are completely flattened, like here. And the most important thing is that secondary minerals, phyllosilicates and carbonates, such as this one, are also flattened. So this would suggest that those minerals were here before the impact occurred. Otherwise, they wouldn't have this weird shape, and we would also see in those cracks a lot of secondary phases that would have precipitated in the shape of veins inside of those. But it's not the case. So we can try to get a scenario for the formation of this unusual meteorite. And this would be that the main alteration event occurred on a primordial parent body. That would have accreted ice heterogeneously. This would account for the variation in the water-rock ratio and for the similarities in the temperature ranges of precipitation. Then one or multiple impacts occurred and disrupted partially or completely these primordial bodies, and some of the debris reaccreted to form a secondary body that would later might be subject to impacts too, and of which some fragment might reach the Earth and give this very unusual texture to this meteorite. So this is what our study does not rule out that impacts might generate second minor event of aqueous alteration. But in our samples, we didn't see any evidence for this at this time. And this would suggest that the main alteration event occur on a single primordial parent body. So the conclusion for those two studies, and I'm right on time, would be that the range of alteration might be wider than what we would have expected, going from -50 to 275 degrees Celsius. And they also seem to share a similar thermal history. So does this suggest that they all have a single primordial parent body that might have been disrupted and might have given other parent bodies later? We can't state clearly on this at the moment. And it seemed that ice was aqueous alteration occurred more in micro environments than fluid flow. And this would be consistent with the study of Boriskino, where we can see that material that might have been close to each other before the impact experienced different geological history while having the same thermal gradient. And finally, we did not see any genetic link between impacts and aqueous alteration, but it does not rule out that secondary event might occur due to the heating led by impacts, but we still don't know at this time. So thank you everyone for your attention. I think it was 45 minutes. So we'll stop here.
Thank you, Maximilien. You have questions? George.
Yeah, so I just wanted to say that with Connell a while back, we studied a wide range of organic solids. study was to basically see. The thing that struck us in this study was torture, because the organic matter, which is a very sensitive thermal indicator, like, it's more or less exactly what you're saying, but from a different angle.
Okay.
The temperatures were on the higher side of what people were saying, but we saw no systematic change in the organic molecular structure from one end of the CM spectrum to the other.
Oh.
So it's very consistent with what you're saying.
It's interesting.
We didn't have the opportunity to work with like Paris or some other meteorites, but a lot of the
No.
meteorites we studied overlap.
Okay.
Really very consistent.
It's weird.
Cool.
So, yeah, it's very, very cool.
Yeah, well, I'm really happy to hear you say it, because I was like, are we missing something here?
No, 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 no. It makes a lot of sense,
like
actually.
very common. CMs are really CM.
Yeah, yeah. This would make sense, but we could have expected very different things.
We
if
did.
And everybody was expecting this, actually. But
we
yeah.
spent months doing this, right?
Yeah.
For a while, it was like torture, because it was always the same thing.
Yeah.
So,
Yeah, I know. I had the same thing. Thank you.
I want to ask a question. Has anyone, you or anyone, tried to do manganese chromium dating on the different lithologies in Boriskino?
Yeah, I did.
And?
Didn't work.
Oh.
Didn't work out. No, the problem is the problem with manganese chromium is that I didn't talk about it, but you have to have carbonates that are heavily enriched in manganese and chromium, and calcites are not, but they are the most abundant carbonates inside meteorites. And the one that we usually date are dolomites, and dolomites are only in the most heavily altered meteorites. And even with this, it exists no terrestrial standard of dolomite with amount of manganese or chromium close to the one in meteorites. And the second problem is that it seemed that what we call dolomites inside chondrites are actually not dolomites, but proto-dolomites. So a heavily enriched calcite heavily enriched in manganese calcite. And it does not have the same structure. And this might influence the matrix effect when you're measuring it. So it's, as far as my work has gotten me, it seems very, very hard to get a dolomite standard, at least using high pressure and high temperature experiments. So I don't know if someone meant it. Yeah.
Right. So these water-rock ratios strike me as quite low. So that you mentioned they rule out hydrothermal circulation. Say something about how much water was present. I mean, one of the issues with these is are these remnants of a comet? The water-rock ratio was very high just intrinsically.
Oh.
Or are these just simply wet rocks?
The problem is, at the moment, we don't, that I know of, we don't have any criteria to state the initial amount of water. And this is one of the big problems, because if we add this, well, we could do so many things. Just using, for instance, the amount of water, the initial amount of water in the composition of carbonates, we can get to the initial composition of the primordial fluid using, I don't know, relic distillation or stuff like this. But we can't, and it's missing. And I've just shown only one calculation for the water-rock ratio, but Ed Young gave another one based on bulk oxygen isotopic composition. And when we do this, we can see that the water-rock ratio for the CM1 lithology is lower than the one for CM2 lithologies. And to me, this is because bulk oxygen values are very sensitive to the history of the sample. If it experiences heat later on, the oxygen composition can be completely changed toward heavier oxygen composition, while it should be lighter oxygen composition. So if you have a tool to estimate this precisely, we are all very interested in it, I think. Yeah?
So following up on water-rock ratio estimate,
Yeah.
so if you're point counting an altered anhydrous,
Oh, yeah.
terrestrial, crustal veins,
Oh.
so would you be underestimating if you're
Completely. No, we have to keep in mind that the way we estimated the fraction of altered rock is really like a basic way to do it. Point counting doesn't give you, we did this using EDS maps and be backscattered electron map. So we've got a little bit of chemical information to try to identify the phase that we're looking at. But I don't know, we could try to get the H2 content inside those different lithologies, maybe or the amount of water using infrared, but this might be subject to water from Earth too.
I'm trying to make a different point. That
Yeah,
so if you're point counting,
it depends because what I said is that using the ADS map, we counted the secondary phases, so calcite, phyllosilicates, and everything as altered, because I was able to identify them using the ADS maps. But it doesn't mean that is highly accurate either. And we should try to get another way without distracting the sample. And this is the main problem currently. We don't want to get one lithology out from the sample and study it independently because we can't. We don't have the 3D information too. So we just have the surface information. And we don't know where the lithology stops below the surface. So it's a first approach, and this is why I said that this estimation have to be taken lightly too, because there are a lot of assumptions behind it. Even on the isotopical information, we assume a lot of the time that it's at the equilibrium that the process occurs, and we don't know if it is the case actually. We always assume that precipitation occurs at the equilibrium. So between water and phyllosilicates, it's the same. And there might be a problem here too. We don't know. And concerning the veins, what I've seen in meteorites is that most of the time the veins inside of those are gypsum, sorry. So I've never seen like quartz vein or anything inside those meteorites. I don't know if it's usual.
Quartz and CIs.
In CIs?
CIs.
I've never seen this.
You can find it in the gypsum and the vein.
Okay.
Okay, if there's no more questions, let's thank Max.
Thank you.
I hope you're around for a while.